Hello, everyone, and welcome to our webinar today on span rigging. I am not Taylor Hamel. I'm Cale Royer. I am the media wizard here at Tree Stuff. He's getting his computer plugged in right now so that it doesn't die in the middle of our broadcast. So I'm glad he thought of that before we started. Just a couple announcements here. We have a couple promotions going on right now. There is the DMM B3GO promotion going on. That is buy 3 get 1 free of any DMM product. So what you do is you take 4 DMM products, put it in your cart, use the code B3GO, and you'll get the least expensive of those things free. So if your least expensive thing is a large impact block, then you get that for free. Hold on, I'm going to mute him real quick while I'm still talking. All right. Don't click on any of these spam comments that are showing up in Facebook. I've been trying to get rid of them. It's difficult. Thanks, Nick Araya. I agree with you. Who else we got? John, John, whoever on on YouTube here, whatever your name is, we have about like 20 some inches of snow, so it's pretty great that I work from home and don't have to go anywhere. Other stuff that we got going on, we still have some more of those Krista Stratting figurines. They're really cool. They're like 3D printed and they're like this big, I think. You can get them for free on orders, I believe, over $500 with the code ROCKSTAR, or you can get one of the Petzl headlamps that we still have, orders over $250 with the code LIGHTMEUP. All of our videos from the Community Expert Contest have been posted. They're up on our YouTube page. If you go to our homepage, there's a little bar at the top that says Community Expert Reviews. Click on that, and you'll get to all those different videos. Watch them. If you like what these people made, give them a thumbs up, and then you can. Sorry, Nick Bonner's calling me. I'm just gonna make sure that my audio is working here. Can everybody hear me? The echo keeps.
I can hear you.
Talking about. Okay, well, I'm gonna get him out of here. A lot of background echo noise. How about now? Give me a thumbs up in the chat if there's no echo anymore. Anybody? Anybody? There's one thumbs up. Some yeps. That's not following directions, Sean. Thanks, but okay, there we go. All right. So, DMM B3GO. Use that to get a DMM product for free. Krista Stratting, Petzl headlamps, Community Expert reviews. Those are up. Watch them. The person at the end of our voting period whose videos have the most likes is going to get $1,000 to use on Tree Stuff. So go help somebody make $1,000. There's some really cool tips and tricks on there. And some really neat videos, so check that out. Our next webinar is on March 18th. That's going to be Shem Kendrick. Hold on. Did I just bitch? Yeah, okay. Shem Kendrick. He's doing modern at-home bonsai. If you've seen his Instagram page, he's got these things all over the place. So it's going to be a lot of fun. You can still get your free CEUs for watching that one. After that, the next webinar that we have kind of slated, we've got him locked down, but the date isn't quite locked down yet. We've got Kevin Bingham coming and doing another webinar on climbing SRT. It's kind of the 2021 update from his first webinar that we did a couple years ago. Super popular, great webinar. He's going to be talking about a lot of new climbing things and a lot of new climbing gear. So check that out. Don't miss it. And without further ado, I'm going to switch it back over to Taylor if he's done digging around and things. Okay, there we go. All right, and it's Taylor Hamel.
Hey, awesome. Hi, everybody. Just making sure we're in frame here. My name's Taylor Hamel. This is Nick Grebe. Nick doesn't have a microphone on, so which is probably a good thing. Yeah, he lost that privilege after he dropped my phone in the last one. Just kidding. That was really fun. Hey, so welcome. Thank you very much. Thanks, Kale. Thank you, Nick. Tree Stuff, as always. It's really fun to do these webinars. Technical issues? We're doing good here so far. Kale, you can hear me all right? Not too loud, not too soft? Sweet. Yeah. Couple little introductions. My name is Taylor Hamel. I'm the technical sort of sales rep for DMM in North America. I've been in the tree industry now for 20 years. Oh my gosh, I'm so old. Yeah, it'll be 20 years this fall. Crazy. So 19, I guess. And yeah, I was a contract climber for 15 years, worked around the world, worked in a few different countries, started hanging out with the Tree Imagineers and got connected with DMM through that. So here I am now doing this kind of stuff. And my intrepid good buddy here, Nick Grebe, is always willing to help. Grebe has been climbing for 16 years and now is working for Minneapolis Parks and Recreation Board, climbing trees and otherwise being a cool dude, helping out there. I think you're doing some training and stuff there too at the park board. So if you don't know Nick, now you do. And thanks a lot for your help. We're of course masked up here. We're gonna, we've both been living our best lives, staying safe and whatever, but this is what we're doing now today. So masking up, do it yourselves too. Quick shout out to NASA and the Jet Propulsion Laboratories for landing Perseverance on Mars. That was pretty sweet, super cool. And some of the stuff we're going to talk about today, span rigging and all that. I might make some comments back to Perseverance because there's a lot of things that we do in the tree world that we shouldn't be doing or that we can do better at, such as managing slack when you climb, dealing with friction, learning just a little bit more about forces and that kind of thing when we're rigging and climbing. And if we can land a rover on Mars and fly a little helicopter around on Mars, then we certainly can tend our slack and learn a few things about friction and force in the tree world. So keep that in mind. If it sounds daunting, don't worry about it. Keep your head down. Keep watching webinars. Chat with your friends, whatever. It'll come together. But let's try to make the best possible decisions when we are working day to day, and keep learning. Just keep going forward. Keep moving. That's what we're here to do. If you've seen a few of my rigging webinars before, some of this stuff is going to be a little review, but I think it's important to keep driving that home. So we will talk a little bit about mechanical advantage briefly. We will talk about forces in redirects and forces, line angle deviations when we talk about span rigging. You can see behind me here we have the new DMM Keanu. We'll go a little bit over how I set it up. We're in this beautiful studio, my beautiful partner, Aisha Formansky. This is Everthine Jewelry Studios. I might give you a brief tour later if we have time, but it's cold as heck outside in Minnesota and everywhere, man, the country's just been getting slammed. So, kudos to everybody hanging in there and working through the cold. But we're not doing this outside, so we're improvising a bit. But hey, there you go. So let's get started. Let's just do a quick intro to the Keanu if you haven't seen it. Then we'll talk about forces. Then we'll get back and we'll show some specific configurations that we use with the Keanu and places that we might use it or might not use it, where it shines, where it might not. Hey, it's a piece of equipment. If you use it once, you'll want to use it again. The more you use it, the more places you'll find to use it, and it'll make your life easier. So what the heck is the Keanu? Well, we called it the Keanu, and maybe we're gonna go up just a little bit on the camera here. Okay, so what is the Keanu? First of all, why the heck do we call it a Keanu? Well, the system that we have set up here is called an English Reeve. Put two and two together, you got Keanu Reeve, man. We were thinking about calling it Christopher Reeve, but that's not quite contemporary enough. So, you know, we got to keep with the times, Keanu. So it's the Keanu Reeve. All right. This system is an English Reeve. It consists of, basically, it consists of a high line. I call it a high line. There's probably other different terms for it. High line, we have a load line here, and we have two control lines, right and left. Now we've got a pretty much flat span here. We've got anchor points at the same height. Of course, you could use this on a slope, anchoring it up high and low. So, you know, running down a slope, something like that, in which case maybe you'd only need one control line. But when we're working on similar height levels with anchors, you know, you got to be able to get it to go both ways. So I'll have Nick just briefly pull up this load on our, actually, we should put helmets on. 1 second. We got all excited and forgot to put our PPE on because we are, even though it's indoors and it's controlled, we're gonna be in a, we're gonna do it right here. If you can pull it, go for it. Oh, my head grew. My head grew over the weekend. All right, so if that's still in frame, you can see that Nick is raising that control line. And he can raise it all the way up and get that pulley sucked right into the little recess there. Or he can lower it down. And at any point, you know, we can move this right or left. So basically that control line is doing the lifting and lowering. The high line is obviously keeping it suspended. And then we can travel along that high line by using the control lines. And at any point along that way, Nick can lower the load, and you can even raise and lower as we are traveling, right? So you've got lots of opportunity there to lift up over obstacles. You know, sky's the limit. Use your imagination. You can go ahead and release that. I think there's about 100 pounds in here. We'll measure it a little bit later. I think we're okay without eyeglasses. We're gonna just say that. So nobody burn me or give me a hard time about no eyeglasses right now, please. Because they're just gonna fog up with these masks and we don't feel like it right now. There's no wood chips flying or anything. We're okay. So that's the Keanu. What does the Keanu replace, or what's so special about it, okay? Well, there's 4 ball bearing sheaves in here. We have quick release pins for easy in and out, different components. One on top here if we want to stick a pulley on top to run a second line. We also have the ability to put 2 Keanus together, so you can run 2 Keanus on 2 completely separate systems, yet contained for example, you know, swiftwater rescue, mountain rescue, things like that. But so why the heck use that if you could just put something else together with a rigging plate and pulleys? Well, basically, if you want to grab that end, this is what we're taking place of here. We got a hub, 4 connectors, 4 pulleys, okay? That's all there, self-contained, 1 unit. It doesn't come apart. You're not losing anything. It's easy to configure. All right, in this case, you know, we'd have our 5th pulley in the load line there. So I'm going to hand that to you, Nick. So put all those components together. You've got, you know, potential for misconfiguration, things like that. You got to keep a sharper eye on it. The Keanu is going to consolidate everything. So that was the brief introduction. There are some other cool modes in the Keanu that we're going to look at a little bit later. And we've got a lot to cover. And let's see, I'm 17 minutes in. Is that correct, Kale? Yep. Okay, sweet. So we've got, you know, hour and a half, and, you know, we'll answer some questions and all of that jazz. I got to watch my ums. I got to watch my ums today. So let's briefly chat about some markings on equipment. I would like to do that quickly first. we'll take a gyro pulley here. And on the gyro pulley, we have, boy, if you can see, going backwards. Okay, in this gyro pulley, underneath the DMM, you can probably see it says MBS and WLL. All right, we've got an MBS of 56 kilonewton and a WLL of 10 kilonewton. All right. Why is that important? Why do we care about it? Well, MBS, no, this, oh yeah, there, he's writing on the screen. Nice. Right before our very eyes. Isn't technology wonderful? I mean, heck, I thought sending a rover to Mars was cool, but writing on the screen live. So, MBS stands for minimum braking strength. Minimum braking strength. So that is defined, and of course I don't have my notes right here. I'll use my memory here. Minimum braking strength is defined as the load above which a piece of equipment is expected to fail when it's new, as designated by the manufacturer, right? So DMM says MBS, minimum braking strength, 56 kilonewton. We're telling you that this pulley, when it's new, that is the load above which this is expected to fail, all right? WLL, working load limit. All right, and the working load limit is also specified by the manufacturer, and that is the load, boy, the technical definition, the load that should never be exceeded with that piece of equipment. It's the load that this piece of equipment is designed to lift, lower, or suspend, okay? And that takes into account what is going to, oh man, I'm really losing it here. So working load limit, 10 kilonewton, all right? That's a 5.6 to 1 ratio here, design factor, whatever you want to call it. And so the MBS is not the biggest load that you should put on this pulley, right? That would obviously break it immediately. The working load limit, 10 kilonewton. That is the largest load this pulley should ever see. Okay, and 10 kilonewton is 1 metric ton. That's about 2,200 pounds. So that's dynamic. It's just the load. So it's dynamic load, it's static load. It's just the load that's the maximum load that this pulley should ever see is the working load limit. Think of it that way. So if you have a 10 kilonewton chunk of wood or whatever that you're lifting with this pulley, you've already exceeded the working load limit, right? Because we have 2 parts of line. So let's cut that in half. 5 kilonewton load on this side, lifting it with a rope. Now you've got 5 kilonewtons on this side. 5 and 5, that equals 10. All right, now you've reached that working load limit without taking friction or any kind of dynamic loading into consideration. You're already there. So it's pretty easy to exceed that working load limit. I think we all have, and I think we need to think about not doing that. So take care. Those questions might be on the exam. Not sure if Kale edited them out or not. Another thing we might come across is SWL, safe working load. And the safe working load is determined by a competent user, somebody in the field. That might be you, it might be your foreperson. And that is the maximum load which the piece of equipment can lift, lower, or suspend given certain working conditions. So it's an older piece of equipment, you've got different environmental conditions happening, and you yourself as that competent operator are determining what that safe working load is. So we've got from the factory new 56 kilonewton MBS, 10 kilonewton working load limit, but I might know the working history of this pulley and I know that it's 10 years old and I just want to downrate that a little bit. So I'm going to make the decision to call it the safe working load, half of that, whatever I feel like. We'll call it 5 kilonewton, all right, instead of 10. So that's up to me in the field or competent user in the field. You might apply that to ropes as well. The rope gets used, change the safe working load as you go. All right. Now, if Nick, without pulling my computer off of the table, can maybe try to get that camera aimed over here at my little load cell. We can do it. I know we can. Oh yeah, we're good. We're good. Yep, that'll be fine. We can also move it closer if we need to. Yeah. We can put the computer on the ground, whatever. All good. Or on this chair. So, can we see those numbers all right? No. I wonder, there we go. We got a light. We're going to just move a little bit closer so you can see the light here. What I have is just a small load cell, and we're going to do a couple little lifts here to describe how friction affects systems, and that's going to apply to how we work with the Keanu. Generally when we're working with the Keanu, well, depending on the situation, in some cases we're going to want less friction, some cases we're going to want more friction, or a bit of friction. Friction is neither good or bad, it just is what it is, and it can work with us or against us. So we'll try to use it to our advantage whenever possible. So what we're going to do here quickly, how much weight do we have here? Probably stick another bag here together. Round turn with 2 half hitches. What's that?
I don't know if it's good to see the reflection of the light.
Okay. All right. I got a couple bags full of stuff here, and we're just about 40 pounds exactly. Almost. We're getting there. You can even. Oh yeah. Let's see if we get 40 pounds exactly. Oh no. Now we're over. That's all right. 40 pounds. Close enough. 39.9. I don't know if you're able to see that on the screen or not, but we've got some bags here. 40-ish pounds. All right, cool. Just so we've proved that's the case. Now, we've all heard or seen or learned about what happens when we drop a load into a pulley, say we're negative rigging, right? If that weight of the piece is, well, in this case, 40 pounds, okay? We're going to need, so we'll have 40 pounds of tension in the leg of line between the load and the block here. That's okay. And in the leg that we're holding, I'm going to need to use 40 pounds of tension in this leg of line in order to affect movement in that load, okay? So that's in a perfect world without any friction. So we would expect, with no friction here, that a 40-pound load would take 40 pounds of input to manipulate it, and we would have a total load on the anchor of 40 plus 40, which is 80, okay? Dude, this writing on the screen is awesome. Yeah, that's really good. Okay. So, well, let's just see what happens, actually. I'm going to just lift this up, and I'm going to step on this rope and hold this aloft, and we're going to see, and I'm going to try to get the rope angle as close to parallel as possible, because rope angle will also affect that. So, what do we got for a load there, Greeby? 60 pounds. 60 pounds, okay? Very interesting. So our load, I'll pick it up a little bit higher so you can see it. All right, we're working as best we can with the camera we got. So the load here, the bags, weigh 40 pounds, okay? I have this suspended. I'm just stepping on it with my foot. And we're showing 60 pounds at the anchor, okay? There's 40 pounds of tension in this leg between the bags and the carabiner, the anchor point. So to get 60 up here would mean that I'm only using 20 pounds. I'm only using 20 pounds on this leg of rope to hold 40 pounds suspended, okay? Well, what's going on there? It should be 40 and 40, right? Well, friction is the answer. There's friction. The rope bent over this carabiner is creating friction. There's a certain amount of surface friction here that's doing some work for me in this case when we're holding this aloft. I need to work less to hold on to this because the carabiner is doing some of that work for me. Now let's see what happens. I'll just lower it in a very slow and controlled manner. Try to get some readings from Nick here. Very slow. 57, so just a slight drop, okay, in force. So basically holding it stationary and lowering it, about the same thing. Now let's see what happens when I raise the load. I'm going to pull down on this rope, put tension in, and I'm going to pick up this 40 pounds off the ground. Okay, 116. Wow, what the heck happened there? All right, and now I'm back to just holding it steady, and we're back down to 60. Okay, so 116 let's just look at it this way. Let's call it 120 because my brain isn't working that well right now, and I wanted to make the math easier. So 120 as I'm raising it. There's still 40 pounds of tension in this leg of rope. The bags are always placing 40 pounds of tension in this leg of rope between the carabiner and themselves. So when we're showing 116 on the anchor point, that means that I'm using 80 pounds, right? Just less than 80 pounds on this leg of rope. We'll round it up to 120 to make it easier. 120 pounds, 40 here, 80 here. All right, so this carabiner, if we do the math, has a surface friction value, if you want to call it that, of 50%, right? There's 50% friction loss in this carabiner with the rope running 180 degrees over its surface. So on the way down, that I'm easily holding, well, not easily, but I'm holding, 40 pounds just with 2 fingers on the way down. Okay. On the way up, I can't even do anything with one arm, okay, because I need 80 pounds of input on the way up. Significant swing in force on the anchor. Now, does that mean that you should never use a carabiner for doing stuff? No, it doesn't. It means that maybe a carabiner might be a good choice if you're trying to lower something in a controlled manner and you want to use less input force and also reduce force on the anchor, because it's just clear as day right here. We're increasing force on the anchor as we lift with friction in place, and we're decreasing force on the anchor when we lower with friction in place. All right, Nick, will you grab me one of those gyros right there? So remember those numbers. 40 pounds, 60 on the anchor when we lower, 120 when we raise. Now this is a very nice high efficiency pulley with a pretty good size sheave diameter on it. We're just going to pop that in place and see what happens to our numbers. All right, so we'll get this up in place, and I'm just going to step on it and not do anything. I like not doing anything. Oh, whoa, wow, it's already harder to step on. Okay, so here I'm just stepping on it. What do we got for a load? 75 pounds. When we had the carabiner in there, our load was 60. All right. Why did that load on the anchor point increase? It's because we have less friction here doing some of that work for us, taking some of that energy in the form of friction. All right, potential energy, I guess I should say. So let's lower it now in a nice controlled manner.
73, 72, 73.
Okay, 73, just slightly less, so about the same. Lowering it and holding it are the same. So isn't that interesting? Even just holding it here, we can see the effects of friction, right? Even when the rope is not moving, because that pulley, it has the potential to move. You know, there's less friction there. If I jammed a stick in there, so or my finger, ouch, that the rope couldn't move at all, we would just say that was 100% friction, right? There'd be absolutely no tension in this leg, still only 40 here. And well, I mean, I could just jam a knot in there right now and show you, right? Should be reading 40 pounds, okay? No tension in this leg. Oh, it didn't work. There we go. All right, so we're gonna lower it, and we had about 70-ish, 75, 73 pounds. Now we're gonna pick it up. 87 pounds. All right, significantly easier to pick up, right? 87, I'm only using 47 pounds to lift 40 because there's less friction there. I don't have to overcome all the friction that was in that carabiner. All right, so you can apply that to natural crotch rigging if you want. Within a certain diameter range, tree limbs have about 50% friction. It's very interesting. So think about that. Another thing that I'll demonstrate here quickly, well, you probably, since we can't see it on the screen, maybe I'll just have Nick count out the numbers for me, but just one more demonstration about friction over a carabiner or a natural fork. Yeah, sure, why not? So we're gonna show, I'm gonna try to get this thing, because Nick's a little gun shy because he dropped my phone last time. We're gonna get real up close here and try to see. All right. Hale, can you see those numbers? Ah, okay. Well, it's just going to light up. So at any rate, Nick, if you would pull those bags up and just suspend them, a foot away. Get on the other side of it. Okay, sure. We can give that a shot. We're moving the stuff around here. Don't get dizzy, everybody. We're good. How's that? Oh gosh, a brighter background. That's going to be okay. There we go. Oh, now I got it. You're good, Kale. You're really good. There it is. Now we can see those numbers. So, yep, Nick's just gonna lift that up and come try to stand directly underneath it. Yeah, there you go. Good. So Nick is holding it steady now. We're showing 65-ish pounds. Now, what's gonna happen, Nick, I want you to release it very slowly, but we're going to see how much you can release without it actually moving. You know what I'm saying? So watch the numbers. Oh, right there, about, keep going. The bag is not moving. It's just barely starting to move at about 57-ish pounds. Now I want you to pull on it, Nick. And now we're increasing force. Now the bag is starting to move at around 97 pounds or so. So go ahead and release a little bit, Nick. So here now Nick is releasing. The bag is not moving. You'll have to take my word for it. I just wanted to show you as, yeah, 60-ish, not moving, not moving. Now put a little pressure on it, Nick. Try to raise it up. And now we're increasing force. The bag is still not moving. 95, 97 pounds. Now the bag is starting to move. So what you're seeing there is a change. Now I'll start talking to you all again. What you were just seeing there is the friction in that carabiner. All right, you're seeing that we have to increase force to try to overcome to lift, and decrease force, that the friction in that carabiner is actually holding that bag in place, even though we are altering how much input we're putting into that leg of line. So that is friction right there manifest. So awesome job. And now let's get the camera reset, and we'll go to the whiteboard, I think, and chat about that for a second.
While you're moving, I've got Brian Tour here is asking what kind of load cell that is and where you got it from.
Okay, well, that load cell, awesome. That load cell is just a quickie thing I bought online quite a few years ago. It's called Kilotech. Kilotech. Kilotech is a couple $100. It's just a scale for weighing small stuff. It's only got a 600-pound limit, and it doesn't have a very fast sample rate, so you're not going to get shock loads and things like that on it. But it's a nice little handy tool to use. I do have, unfortunately, we weren't able to use it today, but I do have the straight point block that DMM has manufactured the body, and then it's sold as a straight point product. And unfortunately, since I haven't been doing any events over the past year or so, this needs to be recalibrated. And so anyway, I was hoping to use this today, but unfortunately, it's gone a little too long without a calibration. So there it is. This straight point block, check it out. And this will read, 2,000 cycles per second or whatever the heck it is. It's a fantastic tool. Straightpoint.com or .co.uk. That's a product. This, last I checked, is around $4,000 with the reader, or, the little digital reader. So, but boy, 60 kilonewton working load limit, awesome piece of kit. But if you're a training facility or you're an arborist interested in looking at just how, what the kind of loads you're generating and things like that, that's an awesome tool. So
here.
Yes, sir.
Hold on. I'm trying to make sure they can hear me. I don't know if I did this. Okay, they can hear me. Travis Hutchin asking about calculating heat from friction. That's probably a bit outside of our purview, but do you know can you talk a little bit about how heat and weather and stuff can affect your friction and your efficiency?
Oh dear. Well,
just
friction. Yeah. So that's okay. I'm not smart enough to do that on the fly. But friction generates heat. Friction dissipates energy. Boy, my physics teacher is going to kill me. But so friction can create heat. So as we have potential energy in a rope system, when the rope travels over that surface, it generates heat because of the friction. So that's one way that friction dissipates that energy, is by generating heat. And I don't know how to calculate how much heat is generated, that kind of thing. And I couldn't tell you if more heat is a good thing or a bad thing. It also has to do with the surface that you're running it over. Aluminum dissipates heat much faster than steel does, for example. Or maybe it's the other way around. But I'm sorry, I don't have that information, but I'm sure a Google search, like most things nowadays. I went to a doctor's office, asked him what was wrong with me, and he just pulled up Google. So Anyway, we're going to keep clipping along here. Got about an hour and 10 to go. So Kale, did we figure out how to do a screen share? Okay, let me see if I can do a screen share here. No, you know what? We're going to skip that. Yeah, you can draw stuff. I'm going to be drawing stuff here too. Oh, I see share screen. What is it? What is it going to share? That's all right. We're going to skip it. We're going to skip it. We're going to skip it. So we're going to do a brief talk about mechanical advantage then in that case. And I'm going to, maybe we can bring the camera right back over here again. Since this is the good place where the anchor is. Okay. We're always on the fly here, you know, it's changing environments and all that kind of stuff. So, refreshing. Okay, don't forget to drink your water. Stay hydrated. It's important. Now, mechanical advantage. I can't see if I'm on frame, so you're going to have to help me out there, Nick. And maybe, how's the light here? We could turn on the lights too if we need to. Okay, I have a mechanical advantage system here, a fiddle block as it were. I have two double sheave revolver carabiners here, revolver rig carabiners. And I'm, of course, using that as a mechanical advantage to lift this load now. So we have this 40-pound load. And as I lift that load by pulling down on this mechanical advantage system, I'm inputting some tension in this leg of line, which will be reflected in the anchor point. So it should be reading slightly higher than 40 pounds. 55 pounds. So it's taken me 15 pounds of input force to raise 40 pounds. Okay. That's a little less than a 3-to-1. Okay. So interesting. Now it's not a perfect science here. It's not a lot of heavy weight. If I turn this around, okay, there'll be a question. Oh boy, here we go. There'll be a question about this maybe. Okay, now I'm lifting up. So I should be taking some force off of the anchor point. So it's 29 pounds, right? So it's taking me roughly 10 or 11 now to raise this 40 pounds. Is my math right there? So I'm basically getting a 4-to-1, right? 10 pounds, 11 pounds of input force to raise 40. Okay. So that is our actual mechanical advantage of this system. Ow. And there's friction. I just burnt my finger on the rope because of friction. How much heat did it generate? I don't know. Enough to hurt. So more than 130 degrees Fahrenheit. And there we go. Now, if we look at a mechanical advantage system, yeah, maybe we'll get a little closer. We're going to do some more camera rigging here. Bear with us.
If you go ahead and buy 4 of those DMM revolvers on Tree Stuff, you will get one free with the code B3GO.
Oh, wow. Nice. All right. Now, this is a mechanical advantage system, a fiddle block. It has 2 double sheave pulleys, as it were. So when I have it anchored here, and I have the 4 legs of line down at the load, and I am inputting, my force is being input here. What is the ideal mechanical advantage without friction, without assuming friction, but in an ideal world, the ideal mechanical advantage, what is the ideal mechanical advantage in this system right now? I've got this fiddle block set up to do some raising. I've got the point here anchored, and we're raising and lowering this load. What is our ideal mechanical advantage? Anybody want to take a guess in the comments? Assuming no friction.
To hear it and to do it.
Yep.
Can you give a quick definition of what you're talking about when you are saying your 4-to-1 ratio?
Sure.
Your 3-to-1? That's
Well, you just gave away the answer, Kale. It's no, it's all good. So, in a simple mechanical advantage system, which is what we have here, a simple system has an anchored set of blocks, or an anchored, we'll call it a block and tackle. So we've got an anchored block that is not moving, and we have a moving block, which is typically at the load because we're trying to move the load. So this is a simple mechanical advantage system. One is anchored, one side is anchored, one side is moving, okay? And when we have a system like that, well, a simple mechanical advantage system can be defined as input force, output force, and reaction force. So my input force
upcoming tree stuff webinars. The next one is Modern Home Bonsai with Shem Kendrick, the creator of the Shem Beaner. That's going to be on March 18th. 2 free CEUs are available. It's going to be a lot of fun. Next up in May, we don't know the date yet. We haven't locked that down, so keep an eye out for it. How to climb SRT with the SRT man himself, Kevin Bingham. It's going to be great. April 15th, we're going to be doing another edition of Modern Chainsaw Training, this time actually out in the field cutting things down with Craig Bachman. He's a great guy. It's going to be very informative, talking about a lot of the science behind cutting trees. May 6th, Casey Snyder is going to be joining us, and he's going to be talking about the Tree Risk Assessment Qualification. It's going to be an overview of what they're going to expect from that test. You can get another certification. On August 19th, right now, that's the tentative date. Upcoming tree stuff webinars. The next one is Modern Home Bonsai with Shem Kendrick, the creator of the Shem Beaner. That's going to be on March 18th. 2 free CEUs are available. It's going to be a lot of fun. Next up in May, we don't know the date yet. We haven't locked that down, so keep an eye out for it. How to climb SRT with the SRT man himself, Kevin Bingham. It's going to be great. April 15th, we're going to be doing another edition of Modern Chainsaw Training, this time actually out in the field cutting things down with Craig Bachman. He's a great guy. It's going to be very informative, talking about a lot of the science behind cutting trees. May 6th, Casey Snyder is going to be joining us, and he's going to be talking about the Tree Risk Assessment Qualification. It's going to be an overview of what they're going to expect from that test. You can get another certification. On August 19th, right now, that's the tentative date that we have, David Anderson is going to be joining us talking about trees, birds, and science. He's done a couple of webinars with us, really cool. He is a PhD in bird science. Some of the current promos that we have going on right now, there's a buy 3 get 1 free on DMM items with the code B3GO. So you put 4 DMM items in your cart, you put in the code B3GO. The least expensive of those is going to be free, whether it's like a DMM Pinto pulley or it is a large impact block. You will get that for free. Also, there's a free Petzl headlamp still.
Okay, we're back. Hopefully everybody can hear me. We had the microphone fail. That's light. So back to mechanical advantage quickly. Nick ever so graciously reminded me that we have a lot to cover, so I'm not going to get too long-winded on this, but it does apply to the Keanu system. So mechanical advantage. Input force in this leg of line. Output force is what I'm generating at the load. And reaction force is what's happening at the anchor point. All right? So, in an ideal mechanical advantage setup, or the ideal mechanical advantage of this system here that I'm using, anchored block here, moving block here, this moving block has 4 legs of line. Okay? You can maybe barely see them on screen there, but there's 4 legs here. Simple mechanical advantage system, I count those 4 legs of line, 4 to 1. That's the ideal mechanical advantage that I'm using in this system right now. Okay?
It's a 4-to-1. Same system, not changing anything other than the orientation of the blocks. Okay. Simply doing that, and now instead of pulling down, I'm pulling upward. Okay. Now this mechanical advantage would be ideal mechanical advantage, assuming no friction, would be a 5-to-1. There is now 1, 2, 3, 4, 5 legs at the load, at the moving block, and this is a 5-to-1, ideally. But as shown on the screen here, you can see it, a 40-pound load, and me making the input, lifting, okay, where the calculator here, the load cell shows that I'm putting in 11, roughly 10 or 11 units of tension to lift these 40 units. So in the real world, the real mechanical advantage is counting the friction that's happening in these pulleys, right? That's a 4-to-1. Ideally, it would be a 5-to-1, but that's not real life, okay? Hope that makes sense. And it goes to show that a system, a fiddle block like this, people call it a 5-to-1. Hey, go get the 5-to-1. We're going to pull that tree over. Okay, well, it's only a 5-to-1, assuming zero friction, which is impossible because we're on planet Earth. It has gravity. Okay, and it also depends on which way you rig it, right? You could be rigging it for a higher mechanical advantage or lower mechanical advantage. It might make a difference. You might need to rig it a certain way in order to get a pull. Like in this case, if I were rescuing somebody in a tree or picking up a load, it's actually quite difficult to pick up this way. It might be better to rig this the other way around and then use my full body weight or get a foot ascender on it or something like that to make the lift easier, even though we're not utilizing the full range of the mechanical advantage system. So think about that. And let's take another example very quickly, because I think this is on the quiz later. All right. The reason, if we're going to ignore these numbers for a minute, and I'm going to go back to some easy math, and we're going to say that this load weighs 100 pounds. All right. So if that load weighs 100 pounds, I'm going to have 20 pounds of tension on each leg of line in an ideal world with no friction. All right, but there is friction, we know that. So let's just say, for example, because it's easy math, all right, I've got a 100-pound load here, and I'm going to input, let's just say I want to input 10. Excuse me. Back up Hamel and start over. Ignore the load for a minute. This load just weighs whatever it wants. But I'm just going to make a point about friction in a fiddle block system, okay? And just to keep the numbers easy, let's say I'm inputting 100 pounds of tension in this leg of rope, okay? 100 pounds of tension. We'll make the math even easier still. We're going to say that each one of these pulleys is super efficient and has 10% friction. And that just for me to make the math easy. These are not actually that efficient. Okay, so 100 pounds of tension in this leg here. It passes over that first pulley sheave, and we lose 10% due to friction, right, in a raising operation. So now this next leg of line has 90 pounds of tension. 100 here, 90 here. That 90 goes up and over that sheave and loses 10%. And now we've got 81 pounds of tension in this leg. And that goes over that pulley and loses 10%. And now we've got 70 something, right? Blah, 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 all the way up until we're finished. Okay, so we're losing some of that tension to friction in each of those sheaves. And that's why the actual output is different than the theoretical output. So hope that makes sense. Now, if we had the choice to build a mechanical advantage system. Obviously, all these sheaves are the same, but if we're building a mechanical advantage system like we do every day, and we're building a Z-rig to pull a tree over or something, it makes sense that we put the most efficient pulley that we have nearest to the input leg. Because if I have 100 pounds of tension here, and I go over, say, a really terrible carabiner or a really crappy pulley or something, or just the rope itself even, it's going to generate a lot of friction. And let's say I'm losing 50% right away. So input force 100, and right out of the gate, the next bend it makes, that leg only has 50 pounds of tension, and then that keeps losing throughout the system. So if I put my best pulley, let's say it's 10% here, 100 pounds of tension, 90 pounds now in that leg, and that can then be reduced throughout the system. So if you only have one really good pulley and you want to get maximum pulling power, put it closest to your input, closest to where you're making that pull. Okay, let's shift over to the Keanu. I got this. You're a good man, Greavy. I'm sure lots of people agree.
Nobody says I'm good with technology, though.
There we go.
I have a question. My question is, when is the Keanu going to be available? And is it available right now?
The Keanu is... No, it is not available just yet. I believe we are turning it out. It's probably in the warehouse just waiting on some last minute paperwork or something. But they are built. They're ready to go. We're just waiting on a few last little hurdles before it can actually start shipping. So I'm really expecting that to happen in the next few weeks. But that's all I got for you.
All right. Sounds good.
Cool. All right. Sweet. So now, Keanu. Like we said before, oh man, I didn't even get to the deflection forces. We'll figure it out. Just watch one of my old webinars and you'll find out all that rigging insight. But what we've got here, let's say we were dismantling a tree on my right, and we're moving the pieces over to the left. We can get rid of this actually for a moment. Okay. Now, so we've got a high line set up, and how do we set that up? Well, let's just take a look. We're, like I said, this isn't a tree. We're using my partner Aisha's studio here. We'll get some more lights on. So yeah, let's. I'll follow you around if you want to take the camera, or I guess I'll take the camera since I'm here talking.
Remove one brain out of that equation.
Okay, so what do we have here? We have a GRCS and a Porter wrap. All right, the high line, which is what's this stuff called? Arbor winch or something. It's Dyneema core, polyester cover, super low stretch. All right. Normally, I would typically run that just over a natural fork in the tree, but since we don't have one here, I'm running it through that small impact block. Okay. And that, of course, is running across through the Keanu, and then it is dead-ended, just anchored at the other side, just with a cow hitch or something like that. All right, so it's stationary over there. Also, you'll notice the load line is stationary over there. We have a couple extra pulleys in place just for fun, but the control line is run through a pulley. We're going to want that through a pulley because we want less friction there. But otherwise, the red and white Sirius control load line and the high line are both just anchored to that spot. Load line goes through the trolley and through the pulley and then into another impact block. And then I've got this green control line here through another Pinto. So it you know, you can get a little crowded at your anchor points there, but you know, that's just life. And there's different clever ways to organize systems. You can connect two things together. I like to keep everything separate just in case maybe there's a sling failure, then you've got you know, some sort of backup. But a point I want to make is, and I've just got a quick trucker's hitch, like 3-to-1 here on a pulley system to tension that high line. You know, a lot of folks want to stick the high line into the GRCS. You don't really need to crank on the high line that much, and you want the GRCS freed up for other things. So I would recommend anchoring your high line in a porta wrap, or just do a poor person's trucker's hitch, or something like that. Excellent. Excellent. Did you drop anything?
Don't start
I'm going to
saying
quit
that
making
now.
that joke. So there we go. What I would do also in this case, I've just left the pulley system in place for the 3-to-1 to tension the high line, but I would take that out. I would get it tensioned, make sure that I had it locked into the porta wrap or whatever, and I would remove that pulley system out of there probably. Just depends on, you know, you're generally not going to be lowering the control line with this system. The English Reeve allows us to raise and lower with the load line and just keep the high line in place. Now, of course, there's lots of options with the Keanu, but in this case, we're going to keep that high line tension. And our anchors are at the same height here, so we need both control lines to pull back and forth. So let's just do a little example here. I think we're probably fine.
You're right. Throw that
Yeah,
down.
we'll just leave it there. I'll try to talk loudly, but Nick, if you want to get it in the GRCS, just so we have some good control with it. So I'll show you. Nick is now tensioning the load line with the GRCS. And now we are raising. That's cool. Yep, that's fine. So that will stay in place there with the GRCS. And now if I want to pull that load this way, of course, I'm just pulling by hand over here. But, you know, we could also use this in a winch. But, you know, in this case, it's not that heavy of a load. I can just easily pull it by hand because we've got less friction. We've got high efficiency ball bearing sheaves in the Keanu. I've got a high efficiency pulley of Pinto up on the top there. So in this case, that I want less friction because I want to use as little input force as possible to get this job done. All right. And again, since we're on a pretty much a flat line here, Nick is going to then be able to pull the other direction and get that moving that way. And now tell you what, pull it all the way over. Yeah, pull it all the way over your way, and then maybe you can even stand on it just for a second. And then what I want to show is that, you know, you can move the load up and down as it goes. So whether you want to take it out of the GRCS or not, that's up to you, however strong you're feeling.
Well, if you want me to go up or if you want me to go down?
Just, you can go down as I pull it. How about crank it all the way up into the cavity?
Yep.
So we'll show another thing here, like this will move without being pulled all the way up into the recess here. But there, you do have that option for maximum height gain. And this also adds, when you get this a little bit, when you get this tucked up in there, there's less bend and less rope contact on that sheave. So you're actually reducing friction a little bit more by pulling it all the way up into the recess. Right? So and now with Nick ready to lower, that might be one too many grabs. Just for my, that's good. So we can either leave it there and pull it, or as we move, he can of course lower it as we go. Right? So lower it down to the ground crew grabs it, brings it all the way to the ground, whatever. And as we're moving, we don't have to pull it all the way up, of course. We can just leave it sit, and we can pull it back and forth. Right, I can just pull this back and forth, and it just rides right in there. It's just an equalized system, as it were. Speaking of mechanical advantage, there's 2 legs of rope here. It's anchored on that end, and we're pulling it through a sheave there. So our ideal mechanical advantage would be 2 to 1. Okay, but in real life, our actual mechanical advantage is going to be slightly less than that, but it is a mechanical advantage nonetheless. That's why you want to use very efficient pulleys on the load line, so you get the benefit of that reduced friction. Okay. Any questions up to this point, Kale? Can you still hear me all right?
Yeah, I can hear you. If you want to step, yeah, there you go, a little bit closer, and we can hear you better. I've got a couple questions. Calculating force on the anchor points when you're using this. Any considerations for that?
Yeah, for sure. You grab the whiteboard. So we're going to do a little whiteboard work here, and I'll work through some of that. But yes, definitely. As you take a rope or 2 ropes joined and start to change that angle, you get differing. Yeah, sure. Sweet.
Nice Vanna White work.
The Vanna whiteboard. Man, Pat Sajak has really been going off lately, hasn't he? He's been yelling at people. I think it's time for Pat to retire.
Really? I haven't seen that.
Yeah, he's going off the rails, man. So when we have, let's say we have 2 anchor points right next to each other. Here with my drawing skills here. And we've got our load here. And we've got a load of 100 units, whatever part of the world you're in. Oh, that's kind of that reflection being.
It glares right in the center. Yeah.
There you go. Cool. All right, 2 anchor points, 100 pounds. We got, let's just say, a rope or 2 ropes. It really doesn't matter. Connected to that anchor point. Straight up and down, we're going to have a load share. We're going to have 50 units on each anchor point. I should draw this bigger, or can you see that? I should probably draw bigger. At any rate, okay, pretty much, if I'm hanging from both arms, straight up and down, each arm is going to be holding half of my body weight, okay? So, I weigh 170 in my dreams. I used to weigh 170 before, So, both of my arms are taking half my body weight. Now, think about an Olympic gymnast, right? And they do the rings, okay? So, as they start to spread their arms out, it becomes more difficult and more difficult and more difficult until you get into the iron cross position, and now you're wiggling and you can hardly hold your arms out there. And that's due to physics, and that's what we'll describe right here. So at this point, straight up and down, 2 legs of line, easy peasy, 50% of the load on each. Eraser around here. Oh, right here. All right, I'm going to draw this next one bigger. Now let's get these anchor points at a bit wider apart. Okay, those are anchor points, and here's our load. Do a different color for the rope. And we're going to call this 90 degrees. That's about 90 degrees-ish. Okay, so in this case now, the anchor points are further apart, and we've got this angle has opened up from 180 degrees, or rather 0 degrees, out to 90 degrees. And in this case, we know that we have roughly 70% of the load on each anchor point. Yes. I'm not losing my mind. That is correct. So now we've got, that's not 7. With 70% on each anchor, which in this case, with the nice easy math of 100 pounds or 100 units, we've got 70 units on each anchor now. So the load hasn't changed. The amount of the load has not changed. It's simply the angle between that rope makes. And as we continue to get wider, like we have in the Keanu example here, try to leave my load in place and we'll set these anchors out even further. We're going to go to 120 degrees. Right. We're just guessing at the angle. All right, so we've got a 120 degree angle here. Can anybody guess what the force will be on each of those anchors now? I mean, I'll just tell you. You just guess in your head. Right, at 120 degrees, it's a magic number where we have 100 units of tension, or 100% of the load on each anchor point. Okay. Interesting. And that peak load that we see there, that 100% load, is putting a load on the anchor in the direction that rope is pulling. Makes sense that would be. There's also a horizontal component that's slightly less, and there's a vertical component that is actually half of the load. I don't have time to go through all of that. You can look back at some of my other webinars and see that information. All right, so this is commonly used in rescue scenarios, search and rescue, and that they tend to keep their high line at 120 degrees or even at 120 degrees or even less if they can, but then it's hard to move around. So at 120 degrees, that you've got 100% of the load on each anchor point, and that your system is within spec, as it were, because the tension really starts to increase as we get flatter. So we'll go super flat, and at about 170 degrees, we're at nearly 6 times the load. We'll just drop these anchors a little bit to make it easy. Rope angle here, almost flat. Why do I keep writing 2? Losing my mind. 170 degrees. And now we have roughly 6 times the force on each anchor. I think in this case it's like 582. If I recall from memory, on those anchors. And that peak force is of course directly along the lines there. Which, when we talk about high line setups, it's important to think about this, because if you have a tree branch here or a trunk, right, and you've maybe got some defect somewhere, all right, you need to think about how much torque you're placing on that. And in which case, it's always a good idea, if you have the room and you can manage it, if we take this rope and run it through a fork in that tree and then back down into some other anchor at the ground, now we don't have that severe torque any longer. If we can keep this angle nice and wide and equidistant, whatever the vocabulary is escaping me now, okay? Now we have a case where we're compressing the tree instead of bending it one way or another. So that's important to consider with anchor points when you're highline rigging. Of course, If we just took this and anchored it to another flimsy little branch over here, that's not really helping us, okay? And if we, and there's all kinds of forces in play. If we took it, ran it through and anchored it down at the base of the tree, all right, we're doing a little bit better. Actually, no, we're doing the same as if we just anchored it up top. And that's in yet another webinar that I did, and I'm not going to get into it now. So if we can open up this angle a bit and compress that anchor point versus torquing it, that's going to be a better option. Did that answer the question in kind of a roundabout way, Cale?
Yeah, I think that's what we were looking for, because we got a lot of people also asking kind of what the best tension to keep your high line at, and what angles that those ropes should be.
Sure. And this is where highline rigging is very complex. And what tension? The tension that you should keep the highline at is the tension which keeps the load above the ground so that you can still work it, right? I would use as the least amount of tension possible to still get the job done, okay? That's another thing about like really pre-tensioning the high line. You're putting a lot of preload on those anchor points and you're not really gaining that much height. So another way to deal with that, if you're losing too much height and you just don't have the anchor point strength to make it work, add in another high line. And I'll show you how easy it is just to add in another pulley to the top of the Keanu. Now you've got two high lines, you get less sag with the same amount of tension. So you just got to be careful. You don't want to over tension things, and that's where something like a straight point block would come in handy, or any kind of load cell really that could take it. But you see that on search and rescue rigs. Oftentimes they'll bring load cells with them to make sure that they're staying within the working load limit of their equipment, right? So yeah, really, I hate the term bomb-proof. But if you've got really nice, good, strong anchors and you're working within the working load limit of your rope, then go ahead and work within that limit. But it's really easy to get ahead of yourself and generate some serious deflection forces in a system like this, especially if you're dumping things into the load line instead of just picking them up and doing static moves. And there's nothing wrong with dumping things into the load line as long as you're staying within the working load limit. I should make that caveat, because another thing about the Keanu is that you can use it to dismantle a tree in 3 dimensions and then move it out of the way. You don't just have to use this to pick something up and move it from point A to point B. You can use it to grab limbs on a tree that you're dismantling and then send them down the road. I wish we could demonstrate that here. We'll do an outdoor demo one of these days. Okay, we got about a half hour left, so I just want to go through a few more little steps with the Keanu, if that's all right with everybody. All good there, Cale?
Yeah, I've got more questions that we can do at the end if you don't answer them while you're talking about it. But I'm good to go.
Okay. Yeah, we'll keep going, and I'm happy to go a little overtime, but whatever. We'll try to get it in without going into overtime. Some quick mods. We'll get in a little closer here, just a tad, so we don't have to move the trigger too much. Oh yeah, that looks good. All right, I think that's all right. Oh, I see.
Just want to let everybody know that if you're going to use that DMM buy 3 get 1 free, you can actually pre-order the DMM Keanu right now on treestuff.com.
Whoa, you can get 4 of them.
You can get 4. You buy 4 of them, and you get 1 of them free.
I should say we do have the Keanu is now up on the website. It's got a product information sheet. You can dig through there. We're working on a video highlighting some of what it can do, and that should be out hopefully next week. And we'll also be linking to some other videos of the Keanu in action. We had some folks, of course, working with it in the validation process. We can show you some of the dismantling that they've done there. One thing along with the Keanu, the gyro pulley has been considered in part of this design. Okay, that's part of why this cavity is the size that it is, and the Keanu has a 50 kilonewton MBS, a 10 kilonewton working load limit. Same here, 10 kilonewton working load limit. These work well, they're compatible, and it's easy to swap things in and out. So let's say we're hauling, we won't bother dismantling this just at the moment, but if we're hauling up a hill, for example, all right? Now, we can do a couple things. We can change this into an English reeve, a Norwegian reeve, and where we terminate one end of the load line into one side of the unit here, and that is really only useful for tree people if you're pulling something up a hill, okay? Because the load line then actually becomes the traverse line or the control line. Another way that we can add some mechanical advantage to this, if we need some, is to add a pulley onto the side. So I'm going to have Nick climb up and reset this, but what I'm going to do is simply pop the quick release pin. I'm going to set a gyro in, put the pin back, and then Nick is going to anchor that. You can probably just use a carabiner too. Why not? Here I had Nick all hot and bothered, ready to tie it into the becket. We're just clipping that back into the becket of the pinto pulley up there. And now we've got, I'll just lift it up and you can pull on the green. How's that? Good. So now we have a mechanical advantage, right? So go ahead and lower it back out if you can. Don't pull that way. All right, so just to show back and forth here, I've got a mechanical advantage now, which is a lot easier to work if I didn't have a winch, or you need a little more power to get things moving. So super cool way to increase mechanical advantage is just pop those quick release pins and set another in. Another quick setup here for a second. You just run that through that top without the rake on it. Sweet. Okay, if I want to add a second access, or rather a second high line, again, that's super easy to do. Just rig it, of course, drop in another gyro pulley, and then that can just go somewhere up there. Hello. Okay, so we don't quite have them separated as we normally would, but easy enough just to set in a second line, and I'll get a close up here when we get that set. All good? Nice. Cool. All right. Anchor this at the bottom. All right, right, so we've added a second line there. Yeah. And of course, I don't have them separated like I normally would, but you can see just with that pulley, we've added a second high line and everything else in place. Two other, I'm going to leave this kind of closed.
So how does that second high line help you out?
So what it does, well, it gives you some redundancy. So in the case of what I was getting at, that's a good segue, Kale, because it gives you redundancy, I guess added strength, if you will. Less sag. If both of these lines are tensioned correctly, then you've got less sag with less overall pre-tension. And in the case of a rescue operation, you need to have two, this is 50 kilonewton, this is an engineered anchor point. If you do want to, you can sandwich two Keanus together with some pins. We've got that available on the website. You can check that out. But in the case here in a rescue operation, I now have two high lines. I've got my control lines. I've got my load line. And I can also add a work line and a backup line for the rescuer. Okay, so if you were dropping over some swift water or in a crevasse rescue or something, you're going to have your litter, which you're pulling your casualty on, is going to be raised by the load line, and you've got two lines for safety here, or as required, and then you also have two lines for your rescue tech. All right, so you're going to have to use your imagination. There's plenty. Just look up English reeve. And you'll see this in action with lots of pulleys and lots of ropes and prussics and all that stuff. And this helps to consolidate all of that. Okay. We'll leave that out. What else should we get to? The English, or rather the Norwegian. So what I'm going to do, let's ditch this.
Can you talk a little bit louder for me?
Louder?
Yeah.
Okay, cool. Sorry, I forgot I don't have the mic on anymore. We're going to do, I'm just going to quickly show you a Norwegian reeve. Yep, I got it. Yep.
He's gone.
I'm out of here, man.
Let's see. What can I draw? Here, I'll try drawing Keanu Reeves while you're... He's got the long hair right now, doesn't he? Kind of has like little beady eyes.
Oh, you're drawing me? Nice.
Ah, Keanu Reeves, not you.
Oh, Keanu.
Yeah.
Little beady eyes. I was gonna say, hey, that's a fair assessment. My eyes are kind of beady.
He's got the scruff.
Okay, Norwegian reeve. Boy, it's hard to see that. I just need to look at the camera, not the screen. Norwegian reeve. Nice thing about the Keanu, it's got quick release pins. Just throw into your figure eight, and away we go.
So that answers one of our questions. Was what kind of knots you're using?
I'm just using figure eights. They're easy to untie, and it's easy to tell when they've been overloaded. I'll keep this line for now. Basically, you're going to be using probably this Norwegian reeve on if we're pulling up a hill towards Nick. Right. So as you pull the load up, he's got a mechanical advantage, right? And then the load moves in that direction, all right? And then when you get to where you're going, then you can lower it down. So it's not something that you're necessarily going to go back and forth with, although you could. But this is just yet another configuration for the Keanu is setting it up as a Norwegian knee. And what we're going to do now is show a configuration with the rigging plate. So let's just bear with me.
So your Norwegian is attaching your load line just to one side, right?
Sure. The load line as set up before through this pulley down into the load pulley again, and then just up and anchored back to the Keanu itself on the other side.
Okay.
And that you can Google it. Check it out. But so what I want to show now, we're gonna drop the high line, and we're gonna show another configuration with a rigging plate. And what we have here, I'll just hold it up and show you. I have another Keanu that's already set with one of our. Is this the XL bat plate? This is the large. So this is the bat plate large. And in order to get it to sit very nicely, we have these little spacers that we've engineered. These will be available for sale as well that fit into the bat plate. So that bat plate just drops in with the pins like that. And now in this case, you could run it on a high line, of course, with some control lines, but then you need to drop the high line every time you want to de-rig the bat plate. So this might be a case, well, or if you had multiple lines, say you're rigging a bunch of limbs out of a fir or something, or a pine, and you could attach multiple slings, and then you just have a control line going downhill with it, right to the chipper, disconnect, pull it back up to the climber, sling, 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 cut, 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 back and forth again. So that's one way to do it. Another thing that we'll show is with two separate anchor points, and we'll get that rigged up in just in real time here for you. So yeah, we'll put this green one through. I'll drop that, and then you can put your green, I'll put the red. Not a mean man, but I'm gonna have to disconnect it here to get it run through. Yeah. Or we can just drop it really. Just hold on to it and I'll disconnect it from up here. All good. Yep.
There's Nick Greeby entertaining us. I don't know if you know this, Nick, but we actually used that footage from the webinar of you throwing the phone out of the tree as like a contest thing. It was guess how far the phone fell, and we just had.
I thought you didn't do that.
Yeah, Nick Bomber was going to ask me to measure it, and then.
Oh, that's right. No, I had the graphics and everything ready, and I think he thought to do something else. That might still be in our pocket for an upcoming contest. Then
I think you should. Oh, I'm all about it. Let me know. I'd be one. I thought it was hilarious.
So what we're doing now is we're taking the same control lines that we've been using. We're going to run these back and terminate them. Okay, I'll do mine first. Nobody's going to see this knot. It's off camera. Got it? Sweet. Okay. Got yours? Yep. All right, so let's just pretend we're hooking up a bunch of slings and stuff. Right? Oh, come this way, Nick. Come on. Uh-oh, we're tangled. All right, and we're just pretending. Lots of different options here. With the back plate, you can tie directly in with rope. We'll do just a quick retrace. Can you hear me all right, Kale? Hello, did we lose you? I can't hear Kale anymore.
Oh, my bad. I was muted on my end. We can hear you. You're just a little.
Out of frame?
There we go. Thanks, Nick.
So we pretended. Now between the two of us, okay, I'll stand kind of out of the way. So now we can navigate this. Go ahead your way, Nick, and I'll let out as you pull in. And we've got kind of flat rope angle here, so it's tough to do. I'll pull my way now. Right, but we can manipulate and move. Go ahead, all the way down. I'm gonna pick up this camera just a little bit. Of course, the wrong one. Yeah, let's try that. Okay, with a little communication between ground crew. And just, you can imagine these slings either holding a log further apart to balance a load, or just multiple slings, multiple branches, and all go toward Nick. So just working as a team, now we can use this trolley on two separate anchored lines. Go ahead, Nick, come my way with a mechanical advantage. And then if we're working in concert, of course, we can lower it into the drop zone. So another cool thing that you can do with the Keanu, and it also highlights the importance of considering friction in your rigging systems. If we just had those ropes thrown over a natural crotch or through a low efficiency pulley or maybe even some carabiners or something, we're going to be working a lot harder. And that was pretty hard to do.
I was going to say, that's almost 50 pounds instead of 100.
That's only 100-pound load, but as we pick that load up and those angles get flatter in that rope, we're experiencing more and more tension in our legs of rope. So, and when it first begins to get off the ground, I'm going to angle this down again if I can. All right, because the rope angle is pretty flat, but like right now, I'm going to call that's about 120 degrees. All right, so as we lift on this right now, we have two parts of line, of course. We have a mechanical advantage ourselves, but there's some friction, blah, 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 what we've been talking about. But as we first get it off the ground, it's relatively easy to hold suspended. And now as we pull higher and higher, and as this rope angle opens up and gets flatter and flatter, it is harder and harder for us. Like I'm sliding across the floor now. The weight of the load itself has not changed, but as this angle here gets flatter and flatter, we experience, we need to input more and more force in order to manipulate. If these were straight up and down from one another, we'd have an super easy time. We'd each only be manipulating half of the load, or 50 units in this case. As this line angle flattens out, then there's more and more tension on those anchor points, more and more tension in this rope, even though the load itself never changes. So, something to think about. How are we doing on time here, Kale?
We are at 47 minutes, so we got about 13 minutes until it's bedtime for the baby.
Yeah, right. Any other questions? Should we?
Yeah, a little bit. Let's see. Had some people asking about the rope usage, how much rope you're gonna need to take into the tree with you, um, and what kind of rope you're using with this.
Sure. Well, it depends on the situation, of course. I would certainly prefer a very low stretch rope. Certainly for the high line, and probably in certain cases for the load line as well. But a little bit of stretch in places is nice to have. The place that you want the least amount of stretch, I would say, would be the high line itself. So Dyneema core polyester cover would be great. That's what we're using for our crane slings and stuff these days. We were just talking about that earlier. So certainly low stretch line for the high line. For the control lines, really you just want something that's gonna be strong enough, particularly in the case where you're lowering something down a slope or raising something on a slope. You're going to want that control line is probably going to be taking most of the force in that scenario, right? When you're just using that control line to gently lower this thing down the slope, so you're going to want some added strength there, But your standard double braid rigging lines, just absolutely fine. If you try to use just a standard polyester double braid line for the high line, you're gonna find yourself with a lot of sag. And you can remedy that, of course, by putting in 2 lines. That'll help somewhat. And really, it's up to you, and it depends on the situation. Now, most search and rescue teams, mountain rescue, that kind of stuff, they're probably trying to travel with ultralight lines, but they still have requirements to meet. Probably NFPA 1983 in the States here, EN 1891 in Europe and the UK. So in that case, they might very well be using EN 1891 ropes like we have here, the KM3 or the DMM's WorkSafe Plus rope, that kind of thing. So the maximum rope diameter on the Keanu is 13 millimeters, so ½ inch. So kind of by design as well, it needs to be compact, and it really forces you to think about the forces that you're putting on this thing. If we made it with the ability to put in 7/8 rope or whatever, you'd be blowing up the sheaves pretty quickly by just dropping massive pieces into the thing. So you always err on the side of caution when you really get things moving on this system. There's lots of jiggling and bouncing. It's never quite as smooth as you think. So to keep that in mind, and particularly when you have a tensioned high line that's quite flat, it really stacks up the forces on the anchor point and the rope itself, when you start getting into that shock load situation. So just everything has to be done with the caveat of, you don't need to be afraid to generate some force, but you just have to make sure that your system is capable of withstanding that force. And just, if you think about the working load limit of the trolley, the working load limit of the pieces of equipment that you're working with, just don't exceed that working load limit, which means that you need to really drastically downsize the piece that you're taking to make sure that with all whatever's said and done with shock loading and jiggling and bouncing and all of that you do not exceed that working load limit.
Okay, with that, when you put the second high line up on there, how is that affecting your load limit? How is that affecting the force on the anchors, I guess, is the big question.
Sure. If the line is, if you have 2 high lines and they're both tensioned roughly the same, it's very difficult to get them under equal tension unless you have a load cell that you're using. But if they are both under the same amount of tension, it will not change the load on the anchor. All right, there it just means you have twice as much rope there. So the ropes themselves will experience technically half of the load, right? Because now you have two ropes, and if they are tensioned equally, they should be sharing that load equally. All right, so each of those have half of the load on them technically, but there's two of them attached to each anchor, so you still have the same amount of force on the anchors. That makes sense?
Yeah. It's just through 4 attachment points as opposed to 2, right?
Yeah,
Is that
sure.
a way of putting it?
Yep.
Okay. All right. And how much rope should you be thinking about?
A lot. It's. I think you really do need quite a bit, particularly in the load line, because you've got. And depending on if you're anchoring it in the tree or you're putting it through a crotch or through a device and anchoring it at the base, that all depends on your particular approach. But yeah, if I'm going to anchor directly to that tree over there, and it's 100 feet span to that other tree, okay, so I've got 100 feet of rope right there, and let's say we're 50 feet up in the air, then I've got to go through a block and down to the GRCS. That adds 50 feet. But then I've got that bight of rope in the middle that needs to reach 50 feet to the ground, so that's 100 feet there. So for a 100-foot span, at the bare minimum, I would say you would want 250 feet of rope. You got to do the math. And this particular, the Keanu is meant to be small, lightweight, compact, relatively inexpensive, and so we don't have the ability to pass knots through it or whatever. We do have the larger Offia trolley that's still in development. There's potential there to have very wide sheaves on that will pass knots, so you can perhaps attach ropes together. So yeah, you're gonna want a lot more rope than you think.
Okay. Let's see. That's about. Hold on. Let me see if we have any. What is the price on this?
I gotta show my DMM logo here.
Oh, there you go.
Right now, pricing is sitting at $6.99 and 95 cents. Yeah, so it's a $700 for the Keanu. It comes packaged. I should have shown you that. I believe the standard Keanu is going to come with 2 pit pins. So, actually, Nick, will you just... So, we've got this cool little packaging here for the Keanu to keep it protected. So you've got a little central pouch that you keep your pit pins in. All right. Keanu goes in there to stay protected. Super slick. And there's room in the top. Well, I've got that back plate in use for your large back plate. I mean, that's worth $700 right there, I'd say. But anyway, yeah, this is how it's going to come packaged, nice and neat. And of course, you can buy extra pit pins for it. You'll have to buy any gyro pulleys that you want to use for it as standalone items. But yeah, that's the Keanu. And like the hub, I would say when the hub first came out, we were showing this earlier. Building English reeds and building rigging systems off the hub. The hub is one of those things that, the more I used it, the more places I found to use it. The hitch climber pulley back in the day, when I started using it, I thought, what the heck is this thing? It's big and bulky. I hate it. I used the hitch climber pulley for like a week and then put it in my bag, didn't touch it for 6 months. And then thought, well, heck, I should start using that again. And then I caught Tree Imagineers in Minneapolis well, that was probably before I bought the hitch climber pulley. It doesn't matter. The point is, like something like this, it's not just going to sit in your truck and you're going to take it out once or twice a year. This is something that you're going to use more often than you think. And once you get efficient at setting it up, and it really doesn't take that much to get these anchor points set up, especially if you have 2 climbers, or even if especially if you're just running it from the high point down to an anchor point on the ground, even easier. Super slick, super easy to set up. And there's nothing to misconfigure, no parts to lose. I mean, you could drop a pit pin, but you're not dinking around with carabiners and pulleys and things like that. So, there's another So yeah, I guess I'll quit spieling on about it. I'll just answer more questions if they're there.
I realize I don't think you said the term span rigging in this. But can you explain a little bit how an English reeve system works in that terminology?
Sure. Just for the record, then, span rigging. I almost said spam rigging. Okay, so span rigging, yes. Span rigging is rigging within a span between 2 points. And what's very cool about the English reeve, well, let's look at a zip line, just a straight up zip line. Anchor the line at the top of the tree, anchor it down by the chipper, clip on some slings with branches, cut those branches off, and zing, there they go, zipping down the line, uncontrolled. Now let's add a pulley and a rigging plate to that maybe, and a control line, so you've got your static line, high line, static speed line or zip line, whatever, that's there. But now you've added an element of control to that with a pulley on top of it. Right? And we can connect our control line and slings and blah, blah, blah. So now we've got, instead of just a free fall zip line, we've got a control line connected, right? That we can control the descent of those pieces as they go down to the ground. And then taking that even a step further with the Keanu, well, and a couple different scenarios that we've shown. And of course, this is all span rigging. I would call a zip line and a speed line, even though they're quite simple, that is span rigging. You're rigging between 2 points. Okay, so here, this is also span rigging. We could be setting this up at the anchor point. It's out in the middle of nowhere. We've got a dead tree that we need to dismantle. We're cutting pieces off of this dead tree and then moving it away without using the tree itself to rig from. The tree is not part of the rigging equation, right? And then take the Keanu, the English reeve, which of course now we've dismantled. But the English reeve takes the speed line or the zip line a step further. Zip line is uncontrolled, speed line is controlled. But in order to raise and lower it, you need to raise and lower the tension line itself. With the English reeve, you have a tensioned high line that stays tensioned the entire operation. And then you've got the load line that's running through the device. And that load line is what allows you to move things up and down. And then the control lines to control the position of the trolley itself. So you've got the ability to raise and lower while you have a fixed height on the trolley itself, or and down a slope as well, a fixed position on that trolley, but still with the ability to raise and lower a load at will, that's, if you want to call it that way, without having to mess with the hollowing itself. Is that?
Yes. Yeah, I think that clears up a lot of stuff here. And then in with that, you've got your English reeve system, your Norwegian reeve system. The Canadians have some sort of reeve system, I'm sure.
Yes, they have the maple syrup system.
The maple syrup system. They're
It is. It's the nicest system. It says sorry to you every 5 minutes.
Yeah, it's all right. I think most of the rest of the questions here are talking about. Somebody asked about using an English reeve or the Keanu for negative rigging.
Right. Yes. I guess I wouldn't necessarily. I would hesitate to call it negative rigging. I would not, for example, now that we've disassembled the thing, but yeah, I would not, for example, have the Keanu in place, take the load line out and pull it above the Keanu, and then drop things from above the Keanu into the Keanu. I would not recommend doing that. First of all, you're going to get very close to the working load limit very, very quickly doing that, and with most things, right? But when we're looking at like the impact blocks, okay, the Keanu has a working load limit of 10 kilonewton. Small impact block has 4 times that working load limit, 40 kilonewton, and our large impact block has 6 times that. Okay, so you're not going to want to be dumping big loads into the Keanu. You can use the Keanu in 3 dimensions, where you have the Keanu set in place. You take that load line and pull it out and rig a branch, put some tension on it, and then cut that branch and pull that branch into the Keanu, and then release it and lower it down. You can do things like that. Of course, you need to keep in mind the tension on your high line. You just do what your system is, capable of handling. But yes, you could certainly set the Keanu, hold it in place with one of the control lines, rig that branch from over there and pull it in, and then let it run down the line. And all doing that smoothly, like Greg Good says, quiet rigging. That's important. Let things run. Don't take massive loads. But do we have a? Can you throw a link to the John Lloyd's video a while back? He did some rigging with one of the Lafia prototypes called Birdland. Do you remember that, Kale?
I do not. Was that us?
Well, you might have shared it at some point, but anybody who's watching, just go on YouTube and look up Birdland. Birdland, Trolley, English Reeve, John Lloyd, you'll find it. He's dismantling some, I believe they're poplars.
I'm finding Bird Rescuer takes in swearing parrot on Fox 5 New York.
Watch that too. Yeah, watch that too. There's stuff out there. We can come up with some links for you, but that's a very, very, very cool showcase of what these trolleys can do and how you can use them in 3 dimensions. It's not just about picking stuff up and moving it, from one part of the ground to the other part of the ground. It's about being dynamic with it.
Gotcha. All right. I think we're about ready to wrap it up there. Do you have anything you wanna plug? Your band? Got a lot of people asking for a drum solo, but
right. Well, this isn't at my studio, so I can't punch out a drum solo. But no, I think we'll keep this pro. Follow me on Facebook, on Instagram, whatever. You'll see what I'm up to. And I guess in closing, I would like to again thank you, Kale and Nick. And I don't know how much Carson was involved in this, but everybody at Tree Stuff is fantastic. Love working with everybody there. Thank you, Nick Reeve, for hanging out today and helping out. Totally awesome. And I guess I would like to say in closing, Also, you know, DMM, greatest company ever. Love it. I've been with DMM full time now since 2016, and just keep hanging in there. Keep checking us out. We're going to be doing a lot more on social media, and we've got a lot of videos in the works coming up. So just keep your eyes peeled for that. I would also like to say, hang in there, everybody. It's been a tough year. We're going to make it. The weather's getting better, at least here in the northern hemisphere, and just just keep being careful. Don't take anything for granted. Stay safe. And when the world opens back up and we can start traveling again, I encourage you to travel. That's what changed my life. Go to another country. Try to work there if you can. Go somewhere where you don't speak the language and hang out with people. It'll change your life. So get out there and do stuff, and we can do it again. And just keep kicking butt and doing good tree work, and make the best possible decision at every step along the way. Just make good decisions. Just stop and think. Don't let anybody pressure you into doing stuff you don't want to do. That's how people get hurt. So that's it.
All right. Great. Well, thank you very much for doing this for us.
Awesome.
And have a nice night, everybody.
Bye.
Bye.